Previously, we were discussing Frobenius series method. Frobenius series method for solving ODEs, particularly second order ODEs with variable coefficients around the singular points. We also discussed what are the singular points. Singular points, and then regular singular points. And irregular singular points. So this method, in fact, help us to find solution of a differential equation around the singular points. Particularly, we can use this method to solve the differential equation around the regular singular points only. We cannot use this method to find a solution around the irregular singular points. In this case, if a given differential, if a differential equation is given, and we need to find the solution around the regular singular point, then we assume that the series is of the form x minus x naught whole raised power r summation n from 0 to infinity cn x minus x naught whole raised power n, where this factor now is additionally multiplied with the power series in order to handle the singular points, regular singular points, in fact. Now let us do an example of this, this method. For example, we need to solve this differential equation. Solve the following differential equation, this one, 3x y double dash plus y dash minus y is equal to 0. Around the point about x equal to 0 or x not equal to 0. Now, we need to first investigate whether the given point is singular or ordinary point. As we see that here we have x, and we know that a2 of x is what? It is 3x. Now, if we put a2 of x is equal to 0, it gives us x equal to 0, because 3x, if we put this thing equal to 0, it gives us x equal to 0. Now, this is your x naught is equal to 0. So x naught is a singular point, Because by the definition of singular point, if we put this coefficient a2 of x equal to 0, then for all x which satisfy this equation, for which a2 of x is 0, those are basically singular points. Now we need to investigate whether the given point is regular singular point or irregular singular point. So for regular, in order to check this, what we do, we assume that small p of x is what? It is x minus x naught power 1, capital P of x. And we assume also q of x is equal to what? It is x minus x naught whole raised power 2, capital Q of x. Where small p of x is what? We have to convert this differential equation first into standard form. Standard form iski kya hogi? Its standard form is y double dash. We divide both sides by 3x, the coefficient of y double dash. So we obtain plus 1 by 3x y dash, and then minus 1 by 3x y equal to 0. Now the coefficient of y dash is what? It is capital P of x, and the coefficient of y is our capital Q of x. Now we put the value of capital P of x here and Q of x here, and then we check whether these two functions P of x and Q of x are continuous and differentiable or not. or they are analytic or not. So small p of x is basically what? It is x, because x naught is 0. X minus 0 over capital P of x is into 1 by 3x. So it becomes 1 by 3 because x cancel, and q of x, sorry, small q of x is, q of x is what? It is x minus 0 whole square, and capital Q of x is 1 over 3x. And it becomes x by 3. Now, you can see that P of x is a constant function, which is obviously continuous everywhere. Q of x is also this polynomial kind of function, x power 1 into some coefficient. These two functions are analytic. They are because they are continuous and differentiable. So these both Q of x and P of x, sorry, both P of x and Q of x, they are analytic functions. What does it mean? Therefore, x naught equal to 0 is a regular singular point. If a singular point is regular singular point, then we can apply Frobenius method. So you can say that thus Frobenius method is applicable and we can find the solution around this regular singular point. So then what we do, we assume that the solution is of this form: y of x is equal to x minus 0 whole power r summation n from 0 to infinity cn x minus 0 power n. So it is xn. So in fact, what we can write here, in order to take the derivative, we have to combine it cn x power n plus r. So this term is basically, it doesn't involve n, where the summation is on n. So we can take this term inside the series or outside the series. It doesn't affect the summation term because it doesn't involve n, and the summation index is n. So we can take this inside and we can add it here because x power r, x power n, so we can write x power n plus r. Now, what we do, we need to take its derivative, and its derivative becomes summation n from 0 to infinity. We have n plus r. It comes down here, cn x power n plus r minus 1. Previously, when we took the derivative of this simple series, the summation, it starts from basically 1 to infinity. But here, it doesn't start from 1. Why? Can anybody tell me? We have a constant phi. No, we don't have any constant. Constant तो पहले भी था. Any other? देखिए, previously हमारे पास series क्या थी? Series was n from 0 to infinity, cn x power n. Okay, this was your series n. If we open this series, what we obtain, it is c naught x power 0. X power 0 is 1 plus c1 x power 1 plus c2 x power 2 plus c3 x power 3 plus so on. Okay. The first term in this series is constant. So when we take the derivative here, this constant term becomes 0 plus c into x, derivative of x is 1. So we get c1 plus 2c2x plus 1. So first term was 0 in the derivative of this series. So the summation starts now from 1. Now the summation starts from n from 1 to infinity n cn x power n minus 1. But in this case, in the case of Frobenius series, what is our series? It is now what? Summation n from 0 to infinity cn x power n plus r. If we open this series, what do we obtain? C0 x power 0 plus r. Now we have r here, x power r, plus c1 x power 1 plus r, plus c2 x power 2 plus r, plus so on. Now, whenever we take the derivative of this series, which is the Frobenius series, this term doesn't become 0. Okay. So it gives us r, you can say 0 plus r, c naught x power 0 plus r minus 1 means r minus 1. So this term doesn't become 0. So that's why the summation index starts again from 0. So you can take the derivative of these terms as well. Its derivative, this comes down here, 1 plus r c1 x power 1 plus r minus 1, and so on. So its derivative, in fact, becomes summation n from 0 to infinity, n plus r comes down, this one, n plus r comes down, cn x power n plus r minus 1. So this is the derivative of this Frobenius power series. The summation still starts from 0 in this case. Now let's come back to our problem, this one. Its first derivative is this. Its second derivative, obviously, it is again summation n from 0 to infinity. And this again comes down here, n plus r into n plus r minus 1, cn x power n plus r minus 2 now. Okay, it's second derivative. Now what we do, we insert y dash, y double dash into the given differential equation, which is given here. This one, y double dash, and then y. And the rest is the same as we did in the power series method. What we do, we collect all the terms. Let me put it here. So what we do now, we put the expressions here. So it is now become 3x in the bracket y double dash. It is what? Summation n from 0 to infinity n plus r into n plus r minus 1 cn x power n plus r minus 2. This is the first term, y double dash, plus y dash is what? N from 0 to infinity, n plus r, cn x power n plus r minus 1. And the last term is again the series n from 0 to infinity, cn x power n plus r is equal to 0. Now, you can notice here that this x and 3, it can goes inside because it doesn't have any n with x. So we can take it inside the summation or outside the summation. So we can multiply x here. X power 1 will be added here. So it becomes n plus r minus 1. Here we have cn x power n plus r minus 1. And here we have x power n plus r. In the next step, let me go over the other board. This one. Okay. Now we can further write that thing x power r. We can take that common because x power r comes in each term of this series. You can see here. Yes, yes. Here x power r, x power r, x power r. I took it inside just to manage the derivatives, and then now again I'm going to take this x power r outside from each series so that it will be simplified. The series, all the series will be simplified, and we can work out in a similar manner as we did in the power series method in order to find the recurrence relations, and then we can find the coefficients of the Frobenius series. So I'm going to take this x power r from each series outside. Okay. Now you can see here x power r, I took it common, and 3x, I'm going to take it inside. So it becomes summation n from 0 to infinity, 3 n plus r, n plus r minus 1, cn x power n minus n plus r बाहर, and n minus 2 था, n minus 1 हो जाएगा यहाँ पे, ठीक है? And the second series is what? It is plus summation n from 0 to infinity, n plus r, n plus r, cn x power n minus 1, plus the third series is n from 0 to infinity, and cn x power n. So this is equal to 0. So we obtain this with the multiplication of x power r. Now x power r cannot be 0. X power r is not 0. Why? X power r cannot be 0 because we have the product of two things is equal to 0. One factor is x power r and the other factor is whole this thing summation of 3 series. In this product, x power r cannot be 0. If x power r is 0, then the initial series which we have assumed here, the initial series which we have assumed here, it will become 0. And it gives us a trivial solution. And we are not interested in trivial solutions. So we assume that x power r, this factor is never 0. Okay? I hope you get it. If you have any question, you can ask me. So that's why we assume here that x power r is not equal to 0. What does it mean? This whole summation factor is, it must be 0 because the product of two factors is equal to 0. And we are assuming that the one factor is not 0, then the other factor must be 0. So in the next step, what we write this whole summation term. Okay. Now, what we used to do in the power series method now, we do the same. What we do, we try to make the exponents of x equal so that we can take them outside common from all the series. X power n minus 1, we have x power n minus 1, we have x power n. Okay. Now, what we check here, that if we have summation n from 0 to infinity, and when we put n is equal to 0, this term involves what? This term starts from x power minus 1. यहाँ पे अगर आप put करें n 0, this term again have what? It starts from x power minus 1. And when we put n is equal to 0 here, this term starts from x power 0. So all the series in this expression must start from the same exponent of x. Means same power of x. For that, what we do, we open up the first terms of these two series so that the series starts from x power 0 in all series. So what we do now here, we open up the first term here for n is equal to 0. When we put n is equal to 0 here, what we obtain 3r and then r minus 1 c0 x power minus 1 plus now the summation n from 1 to infinity 3 n plus r n plus r minus 1 cn x power n minus 1. Now you can see here that this series starts when we put n is equal to 1, it starts from n is equal to x power 0. Now the second series, we also open up the first term here. Plus, we put n is equal to 0 here. What we get here are c0 x power minus 1 plus summation n from 1 to infinity and then n plus r cn x power n minus 1 plus this series is okay. We don't open the first term of this series because it already starts from x power 0. Now this also starts from x power 0. This also starts from x power 0 when we put n is equal to 1. Now we collect all these terms which we have opened here. And what do we get here? We obtain 3r, r minus 1, c naught कॉमन आ जाएगा, x पावर माइनस 1 भी कॉमन आ जाएगा इन दोनों में से. And what we get here plus r, this c naught x power minus 1. Now plus summation n from 1 to infinity 3 n plus r minus 1 cn x power n minus 1 plus the second, this one, summation n from 1 to infinity n plus r cn x power n minus 1 plus the third series n from 0 to infinity cn x power n, okay, this equal to 0. Now here we have x power minus 1 c naught into this. Now what we do now, there is a question in the chat window. Sir, third series से पहले minus sign नहीं आएगा. Yes, you are right. Third series क्योंकि negative है यहाँ पे तो minus आएगा. Minus everyone. Thank you very much. So it is negative because in the equation we have minus y. Now, what we do about these three series, we do the same thing we did basically in the method of power series. Now we try to make these exponents identical in all these three series. Here we have exponent n minus 1, here we have n minus 1, and here we have n. What we used to do in the power series method, we make some substitutions. We put here n minus 1 is equal to some other variable. We try to change the index here. N minus 1, we put here n minus 1 is equal to some k. And then let me call this series as S1 series and this series as S2 series. Now I'm going to make the exponents of x in each series identical. Okay, for that, first series, in this series n minus 1, I'm going to make it equal to n. How do we do this? I hope you know it because we have already discussed it in the power series method. Now the S1 is what? It is summation n from 1 to infinity 3 times n plus r and n plus r minus 1 cn x power n minus 1. Now in this, I assume that n minus 1 is k. If now we are going to change the summation in indices in the summation, n start from 1. If n is 1, if we put n is equal to 1 here, what would be the value of k? K would be 0. And if n is infinity, infinity minus 1 is infinity. So k, it is infinity again. And from here, we can also write what is the value of n. n is equal to k plus 1. Now, everything is set now. Now we are going to change this series into the new series. It becomes now summation. Index has been changed now. It is now k from 0 to infinity, k from 0 to infinity. And 3, instead of n, what we put here, n is k plus 1. So it becomes k plus r plus 1. And here we have k plus 1 minus 1 cancel. So it becomes k plus r. And n, instead of n, we put k plus 1 here, k plus 1, and x power n minus 1 becomes now x power k. Now, as I told you that the summation index is dummy, we can put here p, m, whatever you want. So finally, we can write this series again into summation n from 0 to infinity. 3, we are just replacing k by n everywhere. So it becomes now n plus r plus 1, and then n plus r, and then cn plus 1, x power n. Now, this S1 series has become now this one. Now you can see that the exponent, the power of x is n here, and the summation starts from 0 to infinity. Similarly, we do the same for the S2, series 2, which was basically n from 1 to infinity, n plus r, and cn x power n minus 1. Now again, we assume that let n minus 1 is something m, or you can say it anything, any index, you can say it p, maybe. Okay. If n starts from 1 to infinity, if n is equal to 1, it gives us p is equal to 0. If n is equal to infinity, it gives us p is equal to infinity. And n is what? And n is what? N is p plus 1. So now we can write the series as summation p from 0 to infinity. And n is what? N is p plus 1 plus r. And c p plus 1 and x power p. Now the index is dummy, so we can write here summation again n from 0 to infinity, n plus r plus 1 times c n plus 1 x power n. Now in the second series, the exponent has become now x power n as well. Now what we are going to do, we are going to insert S1 here and S2 here. Okay. Now it gives us, let me put it from here. Now over this equation, the above equation which we have written, it becomes now 3r into r minus 1 plus r c naught x power minus 1 plus summation S1 series n start from 0 to infinity, and it becomes 3 n plus r plus 1 into n plus r cn plus 1 x power n, and then minus, no, plus summation n from 0 to infinity, and n plus r cn x power n, no, n plus r plus 1. So mistake here, मैंने वही दोबारा repeat कर दिया, n plus r plus 1 Cn plus 1 x power n, and the third series is not plus, minus n from 0 to infinity. Cn x power n is equal to 0. We obtain this now. Now we can take common this summation in each series. We can take common x power n from each series. This was basically the purpose of doing all the change of index and substitutions and making the exponent of x identical. Now, if we write this 3r, r minus 1 plus r, c naught x power minus 1 plus, अब सब में से summation common ले लें, n from 0 to infinity, whole common, and what comes inside 3n plus r plus 1, n plus r, n plus r, cn plus 1 plus xn भी बाहर जाएगा. Now from here we can write n plus r plus 1 and the cn plus 1 again, and minus cn will close x power n equal to 0. This is what we obtain. Now from these two factors we can again take common n plus r plus 1, n plus r plus 1. So we can write this thing as n plus r plus 1. Common le le. What do we get inside? We obtain 3n plus 3r. ठीक है, 3n plus 3r. यहाँ पे क्या आ जाएगा? Plus 1. ठीक है, हाँ, this और यहाँ पे cn plus 1 minus cn. So this is what we obtain here. ठीक. Now comparing the coefficients on both sides. Comparing the coefficients on both sides. X power minus 1, यहाँ पे right hand side पे इसका coefficient क्या है? We can write here 0 into x power minus 1 plus 0 into x power 0 plus 0 into x power 1 plus so on. So comparing the coefficients of like powers of x, what we obtain here, you can say that comparing the coefficients of like powers of x or same powers of x of, you can say, x minus 1, x 0, x 1, so on, in general x power n, so on. So xn का coefficient यहाँ पे क्या है? This is all the coefficient of xn, and the right hand side, in the right hand side all the coefficients are 0. So we obtain here, let me, where can I write it? Let me go over there on the other board. Here. What we obtain, if we compare the coefficients, we obtain 3r into r minus 1 plus r times c naught is equal to 0. And from the second term, we obtain n plus r plus 1 times 3n plus 3r minus 1. Okay. Plus 1, sorry, not minus 1. Plus 1 minus, यहाँ पे sorry, cn plus 1, cn plus 1 minus cn. Okay. This thing is equal to 0 again. by comparing the coefficients on both sides. Now this equation, if we call it 1 and we call it 2, equation 1 is called the initial equation. Equation 1 is called the initial equation. And what is this initial equation? Initial equation is the equation of the lowest power of x. Okay, is the coefficient of the lowest power of x in this expression, series expression. Let me show you again the board, previous board, this one. Now the coefficient of lowest power of x. Lowest power of x kya hai? X power minus 1 in this whole series expression. The coefficient of lowest power of x is what? Is this thing. And this is called initial equation in the Frobenius series method. Okay. We can always obtain this kind of differential equation, this kind of algebraic equation in the power series method. Remember that the initial equation is always the coefficient of lowest power of x. And the lowest power of x in all this expression is what? X power minus 1. It is not necessary that it is coefficient of, it is always the coefficient of x power minus 1. It could be x power minus 2, it could be x power 0, it could be x power 1. But that power should be what? Lowest power in the whole expression of the series. Okay, I hope you get it. And this initial equation help us to find the value of r. And what was r? X minus x naught power r factor was basically additionally multiplied with the power series in order to in the Frobenius series method. Now from this equation, from 1, we say that C naught is not equal to 0. Because C naught is an arbitrary constant. If C naught becomes 0, then all the constants will become 0 by using this recurrence relation. Because if we put n is equal to 0 here, 0, and we get C1 here. And when we try to find C1 in terms of C0, and C0 is already 0, so all the constants will become 0, and we get the trivial solution, which we are not interested in. So we assume that C naught is not equal to 0. If C naught is not equal to 0, then we must have 3r into r minus 1 plus r is equal to 0. And we can simplify it as 3r square minus 3r plus r is equal to 0. And 3r square minus 2r is equal to 0. And 3r minus 2 is equal to 0. And from here, we can obtain r is equal to 0 or r is equal to 2 by 3. So we obtain 2 values for r. So these are the roots of the initial equation. Initial equation is what? It is a quadratic equation. Why it is quadratic equation? Because our given differential equation is a second order differential equation. If the given equation is second order differential equation, then initial equation is usually a second degree polynomial, and it must have 2 roots. There's a question in the chat window. Let me see it. Why C naught is not equal to 0? Let me repeat it. You get it. What is, if we assume that C naught is not equal to 0, then this must be equal to 0. And simplifying, this is a quadratic equation, and we must obtain 2 roots, r is equal to 0 and r is equal to 2 by 3. Now, why is this C naught not equal to 0? Because if we look at this second expression, which gives us the recurrence relation, What is this? Now look at this recurrence relation. Now, from the second expression, we obtain Cn plus 1 is equal to negative Cn divided by n plus r into n plus r plus 1. Yeah, ठीक है? No, 3n plus 3r. हम इसको उधर ले गए और ये डिवाइड कर दिया हमने. n plus r n plus r plus 1 times 3n plus 3r plus 1. This one. हमारे पास ये आ गया. अब आप देखें, if ये आपके पास रेकरेंस रिलेशन है. रेकरेंस रिलेशन में अगर Cn को हम 0 पुट करें, n को 0 पुट करें तो क्या आएगा यहाँ पे C1 और C0. अब C0 अगर 0 है तो C1 भी 0 हो जाएगा. अब अगर n को हम 1 पुट करें तो C2 is equal to C1 आ गया. C1 0 है तो C2 भी 0 हो गया. All the coefficients become 0 if we assume that C0 is 0. So C0 must not be 0 in order to get the non-zero values of other coefficients. Otherwise, all the coefficients, by using this recurrence relation, they will become 0 and we'll get the trivial solution, which we are not interested in. I hope you get it. Yes, there is another question. Roots of integral equation must always be real and positive. We'll discuss about the roots. Okay, wait for 1 minute. Now, you can see that from 2, we get this recurrence relation. This is the recurrence relation which help us to find the coefficient of that power series. Are there any other questions? Okay. No. Now, we have 2 values of r from which we obtain from that initial equation. Now, for 2 values of r, we must have 2 different recurrence relations. Okay. For r is equal to 0, we get Cn plus 1. We are now going to insert the value of r here. Okay. When r is equal to 0, we get Cn plus 1 is equal to negative Cn divided by n plus 1 times 3n plus 1. And for r is equal to 2 by 3, we get another recurrence relation, Cn plus 1 is equal to negative Cn whole divided by r is equal to 2 by 3. So what we get, n plus 2 by 3 plus 1 times 3n plus 3 times 2 by 3 plus 1. So from here, what we obtain, negative Cn whole divided by, यहाँ पे क्या आ जाएगा, 3 plus 1, 3 into 1, 3, 5 by 3. अगर 3 कॉमन लें तो आपके पास 3n plus 5 आ जाएगा. हाँ, so it is 3 times 3n plus 5. और यहाँ पे क्या आ जाएगा, 3 3 कैंसिल, 3n plus 3 कॉमन ले लें तो सॉरी ये डिवाइड पे होगा 1 by 3. हाँ 1 by 3 होगा. और यहाँ से आपके पास 3 times n plus 1, ये 3 और 3 कैंसिल हो जाएगा. And what we obtain here, we obtain minus Cn divided by n plus 1 times 3n plus 5. So this is your recurrence relation. Okay. So now let me write it again. Cn plus 1 is equal to negative Cn whole divided by n plus 1 times 3n plus 5. So this is your second recurrence relation corresponding to r is equal to 2 by 3. And this is your first recurrence relation corresponding to r is equal to this thing, r is equal to 0. And this is r is equal to 2 by 3. So if you obtain two recurrence solutions, then you can obtain two different series solutions. If you obtain, why did we take 2/3? Faik Bilal. हाँ भाई, क्यों लिया हमने? Because r is equal to 0 and r is equal to 2/3, they were the roots of initial equation, the first equation, this one. Because from this equation we obtained the values of r. R की value initial equation से आपके पास दो values आई हैं, r is equal to 0 and r is equal to 2/3. So now from the second equation, this equation, we obtain the recurrence relations which involve r. And so if r has two values, then we must have two recurrence relations. One is this and the other is this, corresponding to each value of r. Now, if we have two different recurrence relations, for one, in fact, which we assumed the power series in the start, which was basically this one, okay? Cn has two different expressions. So we must have two different power series for r is equal to 0 and Cn, the first expression, and r is equal to 2/3. So we must have two different series, which will give us
Cn नहीं होगा, मतलब आपने -Cn क्यों लिया है?
कहाँ पे?
Cn नहीं होना चाहिए न्यूमरेटर में.
Yes, plus Cn. Sorry, क्योंकि वहां पे Cn है ना, -Cn है ना ऊपर, यहाँ पे -Cn है तो ये उधर जाके Cn हो जाएगा. Yes, so this is Cn, not -Cn. Thank you. Sorry. So this is अब यहाँ से आपने कोफिशिएंट्स फाइंड करने हैं. फॉर n is equal to 0, पहला कोफिशिएंट क्या आ जाएगा? C1 is equal to what? It is C0 divided by n. अगर आप 0 पुट करें यहाँ पे तो 1 into 1 आ जाएगा. 1 into 1 means C1 is equal to C0 divided by 1 into 1. We have to make a pattern, so leave it in this way. n is equal to 1 करेंगे तो आपके पास C2 is equal to C1 divided by अब n1 है तो आपके पास क्या आ जाएगा यहाँ पे 2 into n1 है तो 3 into plus 1, यहाँ पे 4 आ जाएगा. ठीक है. Now it becomes C1 is in fact what? It is C0 divided by 1 by 1. So it becomes C0 divided by 1 into 2 into 1 into 4. This and this. Okay. And similarly, you put n is equal to 2 here. N is equal to 2. What we obtain? Let me erase this thing only so that we can generalize that expression. For n is equal to 2, what do we obtain? C3 is equal to C2 all divided by, what was the expression? 2 है तो यहाँ पे 3 आ जाएगा और यहाँ पे 6, 7. ठीक है. So it becomes 3 into 7 and C2 is what? C2 is 1, 2, 1, 4. So it becomes C0 1.2.3 into 1.4.7. ठीक है. I'm trying to generalize it. So for and so on, Cn would be what? I'm going to generalize it. So it is C0. यहाँ में देखिए C3 है तो 1, 2, 3 and C3 है तो 1, 4, 7. So if we have n here, it would be n factorial, because n factorial we must have 1, 2.3.4 so on dot n. ठीक है, into 1.4.7 and so on. यहाँ पे basically क्या है? When n is 0, we have 1. When n is 1, we have 4. So it should be 3n plus 1. Okay. And further, this can be written as C naught whole divided by n factorial times 1.4.7 dot so on dot 3n plus 1 this. So this will be your Cn. You have to generalize it yourself. There is a question in the chat window. Let me see the question. Sir, in सब terms के साथ minus sign होगा? नहीं, sign नहीं होगा negative. वो ऊपर जो है वो हमने negative गलत लगाया हुआ था. That was positive in fact. So this is or in general Cn. And this these coefficients are corresponding to r is equal to 0 in fact. R is equal to 0. Similarly, you can find the general expression for r is equal to 2 by 3. That would be of similar kind. So if you obtain C and this for corresponding to r is equal to 0, then our power series will be of the form what? Let me write it somewhere. Maybe not here. Here. And the power series is what? Y of x, the solution series. X power r, summation n from 0 to infinity, Cn x power n. ठीक है? अब x power क्या है? X power r 0 and summation पहला कोफिशिएंट जो है इसका आप सेपरेट कर लें C नॉट का. ठीक है, बाकी आप रहने दो बेशक, इसको लिख दें ये C नॉट x पावर 0 प्लस समेशन n फ्रॉम 1 टू इंफिनिटी Cn x पावर n. ठीक है, बिकॉज C नॉट हमने अस्यूम किया हुआ है कि ये नॉन जीरो है. आप इसको एक्सपेंड या आप सारे को भी एक्सपेंड कर सकते हैं. देन व्हाट डू वी राइट हियर, बिकॉज n वेरीज फ्रॉम 1 टू इंफिनिटी. यहाँ पे n को 0 लेंगे तो C नॉट जो है वो C नॉट 0 नहीं है तो C1 किसके इक्वल है? C नॉट के इक्वल है. तो फिर आपके पास क्या आ जाएगा यहाँ पे? x पावर 0 अगेन सेम, x पावर 0 इज दिस C नॉट प्लस यहाँ पे समेशन n फ्रॉम 1 टू इंफिनिटी. एंड Cn की वैल्यू क्या होगी? Cn की वैल्यू हमने अभी फाइंड की है, which is basically this one. In terms of C naught, it is C naught divided by n factorial 1.4.7 so on 3n plus 1. This times x power n. This one. ठीक है. अब यहां से C नॉट को भी अगर आप कॉमन ले लें तो आपके पास क्या आ जाएगा? C नॉट टाइम्स 1 प्लस समेशन n फ्रॉम 1 टू इंफिनिटी x पावर n होल डिवाइडेड बाय n factorial 1.4.7 so on dot 3n plus 1 this. So so this is your first solution. This is your first solution. Why? 1 of x. Okay, this is your y1 of x, and C not equal to 0. You can basically eliminate it. It doesn't matter. So this is your first solution. Now, what you do corresponding to r is equal to 2 by 3. Again, you find the coefficients using this recurrence relation. You can find the coefficients and you can generalize them. You can obtain the second series solution. Is there a question in the chat window? No. Similarly, you can find the other solution using this second recurrence relation. जी बेटा.
सर ये जो आपने ऊपर y of x के अंदर ये जो x पावर r समेशन Cn x पावर n है, ये जितनी भी हमारी सॉल्यूशंस होंगी रेगुलर सिंगुलर पॉइंट्स के लिए वो सब इसी फॉर्म की होंगी.
Definitely. About the ordinary point 0, sorry, about the singular point x not equal to 0. ठीक है, यहाँ पे तो x नॉट 0 है ना, तो इसलिए x पावर r कर दिया हमने. इन जनरल ये क्या है? इन जनरल इज बेसिकली इट इज x माइनस x नॉट होल रेज पावर r summation n from 0 to infinity c naught x minus x naught whole raised power n. ठीक है, because x naught is 0 here, so we put it 0 here, x power r and x power n यहाँ पे आ गए. ठीक है, इन जनरल फ्रोबेनियस सीरीज की जो फॉर्म है वो यही सीरीज होती है. ठीक है, we insert the derivatives of this series into the given differential equation, we try to simplify it, we try to find the initial equation, we find the value of r, and then now there are several cases from the initial equation. You know that the roots could be what? The roots could be real and distinct, roots could be repeated, maybe equal. From this initial equation, what we had obtained, we obtained a quadratic equation. ठीक है, यहां से आपके पास quadratic equation आ गई है. ठीक है, let me discuss about the roots now, roots of that initial equation. Corresponding to two roots, you must obtain two linearly independent power series. Linearly independent power series जब होंगी तो आपके पास जनरल सॉल्यूशन होगा, यू कैन राइट इट इन टर्म्स ऑफ कांस्टेंट प्लस फर्स्ट सॉल्यूशन प्लस कांस्टेंट सेकंड सॉल्यूशन. ठीक है, that depends on the roots of this initial equation. So it is basically 3r square minus 3r plus r, so it is 2r. So it is basically a quadratic equation which gives us r is equal to 0 and r is equal to 2 by 3. Now, you know that this quadratic equation can have real roots as well as complex roots. We are not considering here complex roots. We only consider real roots. But in real roots as well, we have three cases. Case one, when roots are real and distinct. When the roots are real and distinct, plus they do not differ by an integer. You can say that the difference is not a positive integer. Okay. In this previous case, यहाँ पे देखिए, they are distinct, real and distinct, and their difference is not a positive integer. ठीक है, you can see that. अब यहाँ पे difference देख लें, 2 by 3 minus 0 is not a positive integer. Okay. In that case, we obtain two distinct, or you can say linearly independent series solution. y1 and y2. ठीक है, and the general solution, you can write it as c constant, maybe c y1 of x plus d y2 of x, where these two series y1 and y2 are two distinct or linearly independent power series. If this is the case, roots are real and distinct, plus their difference is not a positive integer, which was the case in first example which we have done earlier, this one. Okay. This was the case one. Now, the case two is when the roots are real and distinct. Case two is roots are real and distinct but their difference up case 2 or 3, basically they are almost identical, but there is only minor difference. Roots are real and distinct, but their difference is a positive integer. In this case, we cannot obtain two linearly independent power series or two linearly independent solutions. In that case, uh, in this case particularly, in this case, the roots are the second series is basically a constant multiple of, or you can say it depends on the first series solution as well. In that case, uh, we are unable to find the second solution. Okay. In that case, we are unable to find the second solution of the given differential equation. But if the given differential equation is of second order, then we must have two linearly independent solutions in order to write the general solution. I hope you know it. What we do in that case, in this case, the second series, there is a theorem, and in that case, we can find the second series uh, in this form: constant times y1 of x times ln of x plus summation n from 0 to infinity bn x power n plus r r2 r2, where b naught is not equal to 0, where and c, this c is a constant. The second series solution will be of this form. And how can we find it? We assume where y1 is what? It is the first series solution. Y1 is what? It is the first series solution, which we have already obtained. Okay. Now, how to obtain this second series solution? There are two methods of finding second. Either you put this series into the given differential equation and do the similar procedure in order to find these unknown coefficients bn. ठीक है, जैसे कि हम फर्स्ट सीरीज को एक डेरिवेटिव लेते हैं, दो डेरिवेटिव लेंगे, हम उन दो डेरिवेटिव्स को अब क्या करते हैं, गिवन डिफरेंशियल इक्वेशन में पुट करते हैं, फिर सारी सीरीज का सम की टर्म्स एक्स के जो एक्सपोनेंट्स हैं वो सेम करते हैं, समेशन बाहर लेते हैं, एक्स पावर एन बाहर लेते हैं, आपके पास रेकरेंस रिलेशंस आते हैं, एंड देन यू फाइंड द रेकरेंस रिलेशन एंड देन you get the series. Similarly, you can put this series y2 of x, this whole series now, take the first derivative of this series, second derivative of this series, you put all the values of this series into the given differential equation and simplify, then you can find the recurrence relations in order to get the values of these b's, which are unknown constants. And it is basically a very lengthy process. You can see this series involves, in fact, two series. Y1 of x is a series, and Vn of x is a series. But you don't have to put here the series, because Y1 is a solution. It is obviously, it will obviously satisfy the given differential equation. So when this is a solution, when you put this part of this series into the given differential equation, this term will be eliminated because y1 is a solution. That can you can simplify the calculations by assuming that y1 is a solution. Okay. I hope you can do it. Let me we'll discuss it later on in detail. Let me show you the third case. In the case 3, sorry. In case 3, when the roots are real and equal, In case 3, roots are real and equal, means R1 is equal to R2. In that case also, we are unable to find the second solution of that differential equation. Okay. What we do in that case, the solution would be of this form. It is almost similar as in the case 2, except the constant in the first term, y1 of x, natural log of x, plus summation n from 1 to infinity, bn x power n plus r1 here. Previously, in the previous case, you have r2 here and a constant here. But in case 3, there's no constant here, and here you have r1, because r1 is equal to r2. So this would be the second solution of the given differential equation, assuming y1 is the first solution, first series solution of the given differential equation. How to find the second solution? You take the first derivative, y2 dash of x is equal to what? You have to take the derivative here. You have a product rule here, obviously. So it becomes y1 dash of x, natural log of x, plus 1 over x, y1 of x, plus here summation, not 1, it is 1 or 0. It is from 1, I think. Check here whether we have 0 here or 1. I'm not sure. यहाँ पे 1 है अगर तो n from 1 to infinity, n plus r1 times bn x power n plus r1 minus 1. You take the second derivative as well, y2 double dash of x. I hope you can do it. You have y2 dash, y2 double dash. You put all these expressions into given differential equation and rearrange the terms and try to find the recurrence relations in terms of bn in a similar manner we did in the previous example, and you try to find the recurrence relations in order to find the coefficients bn. And then you can obviously, after finding the coefficients bn, you put them here in this series along with the y1 series. This will be the solution, second solution of the differential equation. If you obtain the two linearly independent solutions of the given differential equation, then you can write the general solution as y of x is equal to some constant times y1 of x, first solution, some other constant times y2 of x, which is the second solution. So this will be your general solution. Okay, having two unknown parameters which can eventually obtained by using the initial conditions given in the differential equation. So it's a bit lengthy, but these are the methods. We have to know it.
Sir?
जी बेटा.
Sir, I checked and it's n is equal to 0 से लेके infinity तक for real and equal. Also,
ठीक है.
sir,
It is from n is equal to 0. This is from n is equal to 0.
Yes, sir.
Okay.
Sir, also उन्होंने एक website पे लिखा हुआ है कि they're both when they're separated by an integer and when they're real and equal. तो उनकी solution y2 एक ही तरीके से find होती है, लेकिन एक में हमने constant consider किया और एक में हमने नहीं किया.
हाँ जी.
Why is that the case?
In fact, these involves basically a theorem and a very lengthy and complex derivation, which I'm avoiding here by looking at the content of this course, maybe scope of this course. You should read those things in upper level course, I think, ordinary differential equation, which is MATH210 course. MATH210 hai, I don't remember exactly the code of that course, but these things, the proof of these things or the derivations of these things is beyond the scope of this course. Okay. But if you are interested, I'll provide you the derivation or the theory involved in deriving all these things. You can have a look at that. Okay.
Okay, thank you, sir.
Fatma, okay? Because that involves a lot of time and we don't have much time to discuss those things. But it is not necessary that you use these methods. There is another method you can use in order to find the second solution. That is, I think, more simple than this solution, this type of solution. You can use the method of reduction of order formula. आपके पास है ना हमने we have already discussed the method of reduction formula, which is in that case the formula is y2 of x, y1 of x, whole integral e raised power negative integral p of x dx whole divided by y1 of x whole square dx. Okay. Now inserting the first series here and here, you have the value of p of x. This is your very simple expression. Here you have y1 square. That is a series. You can take it in the numerator, and then you can use the binomial theorem or binomial series kind of thing in order to simplify this thing. And then integrating this expression, you can obtain. And after multiplying that expression with y1, you can obtain the y2 series. You can use this method of reduction of order formula in order to find the second series. If you are unable to find the second solution in the case 2 and case 3, either you use the case 2 and case 3, the series expressions given in those case 2 and case 3, or you can use this formula, which is the method of reduction of order formula, in order to find the second solution if the first solution is known. हमने ये पहले डिस्कस किया हुआ है कि this formula can be used in order to find the second solution of the differential equation if the first solution is known. So we can use this formula directly without discussing any other cases. Either the roots are equal or not equal and they differ by a positive integer. In both that cases, we can use this formula in order to find the second solution directly. ठीक है ये नोट्स में मैंने कहा हुआ है कि this kind of example is given on the page 328 in the book of Dennis G. Zill. This is in fact the example 5. You can use that method to find the second solution as well. Okay, I'll upload these notes today and I'll include some of the exercises. Also for this method, you can try these examples and exercises given in my notes as well as in the book. I hope you understand it. If you have any question, you can ask me right now or in the next lecture if you want. Otherwise, I'm going to stop today till here and we'll discuss next things in the next lecture. Any question? If there is no question, then okay, take care. Allah Hafiz.